Yes, thank you very much. So first again, let me say that I'm very sorry that I wasn't able to make it in person. I really wanted to attend, but unfortunately I got a very bad bronchitis just the day before I left. And so now I have to do it on Zoom. And anyway, I'm very glad that we managed to find the solution. And so what I'm going to tell you is I'm going to talk about geometric phases in the context of quantum gravity and ADS-CFT correspondence, and in particular investigate their implications for the von Neumann algebras that have been discussed recently in this context. And so I'm going to begin by showing some relatively straightforward models in quantum mechanics, and then show that they have some mathematical features that are actually also realized in the quantum gravity setup. And so the entire talk is placed in this relation between geometry and entanglement, which of course is also the topic of the entire conference. And I'm also going to focus on wormholes and the factorization issues in the ADS-CFT correspondence. So I'm going to begin by explaining briefly the Berry phase as an example of a geometric phase in quantum mechanics, and show how it's related to von Neumann algebras in the quantum mechanical context, and then move on to 2D gravity first to show how the same features arise there. I will then also turn, to two-dimensional conformal field theories and their gravity dual. I'm also going to show you that we can also have slightly more complicated quantum mechanical models, like a particular spin chain model where these von Neumann algebras also arise. And I think that's another example of a very nice relation between these mathematical, or a realization of these mathematical concepts, not just in quantum gravity, but also in more straightforward many-body models. Okay, so as everybody in this conference knows, the wormholes provide a relation between entanglement and geometry in ADS-CFT, and this has been investigated now for quite some while already in the ADS-CFT context. And so here our starting point is that the concept of a wormhole can also already be present in very simple quantum mechanical models, as I review. And already calculating partition functions leads to wormhole-like structures in performing the calculation. And so one of the main points of this talk is that the Berry phase provides a geometrical picture of how actually the degrees of freedom entangle. And so that's one of the new aspects that I'm going to show to you. And so in particular, this is relevant for characterizing the factorization puzzle, and we can actually follow a somewhat mathematical approach to missing information in the factorization puzzle. So then one of a second important result that I'm going to show is that for the von Neumann algebras, the definition of the trace actually requires the Berry phase to vanish, which gives a very concrete handle of relating the geometry of phase spaces and the algebraic quantum properties of the associated quantum system. So that doesn't only work in quantum mechanics, but also actually in conformal field theories, as I mentioned. And finally, I'll comment a little bit on the spin chain model. Okay, so let me show you the papers this is based on. And so mostly this is a series of papers where we looked at Berry phases in quantum mechanics, ADS3, CFT2, the relation to von Neumann models and von Neumann algebras and the spin chain models. And it's been done with my collaborators here in Würzburg, and notably Shovik Banerjee, and also Moritz Dorband, René Meyer, Annalena Weigelt, and Giuseppe Di Giulio, Pablo Bastero. So I'm very grateful to all these wonderful collaborators. All right, so let me begin by a very brief review, putting things into context. So the starting point of everything is the eternal ADS black hole, of which you see the conformal diagram here in Kruskal coordinates. And so I'm going to work with non-traversable wormholes here. And one important point that will show up in the analysis is that there's actually a singularity in the time coordinate here, in the sense that the time-like killing vector switches signs at the horizon. So in some because time goes in this direction for the right-hand boundary, and in this direction for the left-hand boundary. And so this singularity will actually lead to a non-exact symplectic form in the phase space, and that will be at the origin of many mathematical properties that we are going to study. So you should keep this picture in mind with the two CFTs on the two sides. And so, as probably most of the people in this audience are aware, there's a suggestion that the eternal black hole in ADS is dual to two copies of the boundary CFT, which are entangled in the thermophile double state. And so let me just remind you that the thermophile double state is the purification of a thermal state of one of the CFTs, and can be written in such a way with the two bases of the two Hilbert spaces on both sides. And so if we trace over the states in one of the two CFTs, we get a thermal density matrix for the other. And this is, of course, a concept which has been around for quite some time. Okay, so also very well known to this audience should be the factorization puzzle. And let me just very briefly recall. The two CFTs have disjoint Hilbert spaces, since there is no interaction between them. So for the CFTs, we expect such a factor structure for the entire Hilbert space. So there's one Hilbert space for the left-hand CFT and one for the right-hand CFT. However, the wormhole Hilbert space, so the quantum gravity theory here in the interior, does not have a factorizing Hilbert space, and so there's an apparent contradiction, and that's been the source of many very fruitful investigations over the last couple of years, and a lot of progress has been made, and I will show to you how this Berry phases contribute to this issue. Okay, let me very briefly mention, since I'm going to talk about quantum mechanics briefly. So here I'm taking these examples proposed by Hermann Verlinde a few years back about realizing wormhole-like structures already when you evaluate partition functions. And so also already in very simple quantum mechanical systems, if this is the partition function of a particular quantum mechanics model, then writing this as an integral path integral in phase space, we generally have this expression here, where the integration region is this disk. Here the circle is the compactified time direction, which gives us the temperature. And so in phase space, we have generalized coordinates and momenta, which are associated to a symplectic form. And now there's this crucial feature that if this symplectic form is exact, which means that you can write it as an exterior derivative of another form, then you can use Stokes' law, and you can turn, this contribution to the path integral into another boundary term, and then you would have factorization. However, if the symplectic structure is not exact, then you cannot do that. And so then, for instance, if you calculate a correlation function of 4 of these partition functions, then you get such a connected integration region, which has this very wormhole-like structure. Okay, so now let me explain how the Berry phase enters this game. And so, of course, the Berry phase is something which is very well known in the condensed matter context, in context of topological insulators, for instance. But here we're going to use a rather mathematical approach to these geometric phases, which is based on the so-called Maurer-Cartan form. So consider a connection on a group manifold M, which is defined for any group element sigma. And so this connection, which is this Maurer-Cartan form, then takes this particular form. And from this, you obtain your Berry connection by, so if you consider some particular quantum field theory or quantum mechanical model, by looking at the ground state expectation value of this form, which is given here. And then the curvature that is associated with this form, you obtain from the so-called Kirillov-Constant symplectic form, which is given here. So it's the exterior derivative of this Maurer-Cartan form. And then, so this would be our Berry curvature. And then the Berry phase in the case where we are just, for instance, looking just at SU2, would be an integral over the sphere over this curvature. So that's a simple example from quantum mechanics. Sorry. Okay, so I'm going to go into more details on the next slide, but just to finish this review part, let me mention that I will also talk about the von Neumann algebras, which have received a considerable attention in the context of ADS-CFT in the last couple of years. And so this goes back to von Neumann already almost 100 years ago, and it's a concept of algebraic quantum field theory, which can be used for classifying operator algebras with respect to their entanglement properties. And so there's 3 types of these algebras called type 1, type 2, and type 3. And so type 1 is what we usually have in quantum mechanics when there's a finite dimensional Hilbert space. So where the density matrix has a trace and this trace admits irreducible representations. So we have a well-defined finite entanglement entropy. And then type 3 is what normally happens in quantum field theories where there's no such trace prescription. So for instance, we are very familiar with the von Neumann entropy, which for instance arises for conformal field theories in 2 dimensions. And these always require a cutoff. And of course, the expression is infinite when the cutoff is taken to infinity. And then there's this intermediate type, which is called type 2. And so this means that the algebra admits a trace prescription, but this does not act irreducibly. So this means there are only particular states for which you can define a trace. Okay, so most of what I'm going to talk about is to relate the Berry phases and these von Neumann algebras. Okay, so let's first do this for quantum mechanics now. And so let me start with a very simple example, which is we take a very simple Hamiltonian, which is a Hamiltonian for 2 interacting spins. So I have 2 spin-and-a-half particles that are coupled to each other with some coupling constant J. And then we assume that one of them is actually in a magnetic field, B. So physically, that would mean that we consider an electronic Zeeman interaction for the hydrogen atom. And now we can just solve the Schrödinger equation for this Hamiltonian and then find the ground state that actually looks like this. And so most importantly, here's this coefficient alpha, which is given here. And essentially, okay, there's a tangent involved, but essentially you can view this as the ratio of the mod of the magnetic field and this coupling strength that appear in the Hamiltonian. And yeah, so to get anything non-trivial, it's very important that we have this interaction between these 2 spins here. Okay, so then the projective Hilbert space of the physical states of this model is CP3. And we can perform a so-called Schmidt orthogonality decomposition, which is a standard procedure in quantum mechanics, as is shown here. And so then essentially we obtain 2 different coefficients for the diagonal here with spin up and spin down. And so for the context of von Neumann algebras and also later to make a map to the black holes, we note that there's some very interesting structure here, which is the so-called entanglement orbit. So that's a manifold which contains all the states which have the same entanglement entropy. Now, in this simple model, again, in the quantum mechanical model that I'm talking about, the entanglement entropy looks like this, with these Schmidt orthogonality coefficients. And now the result, you can calculate this and you get this result. Again, alpha essentially is the ratio of the magnetic field strength and the coupling strength. Now, there are 3 different cases that you can distinguish. So the first one is if there's no entanglement between the 2 spins. So then this is the case when they're not coupled to each other. And in this case, the entanglement is 0, and then actually this entanglement orbit is factorized. So we have a product of 2 CP1s. On the other hand, if we have maximal entanglement, and so this means this is the strong coupling limit when the coupling is J is very large, then the entanglement entropy is log 2. And then essentially we have a non-factored entanglement orbit, which is SU2 mod Z2, which is RP3. And then there's lots of intermediate cases where alpha takes intermediate values, and then we get structures that look like this one here, given here at the bottom. And so already here we see that there's a relation between the factorization properties and the entanglement. Okay, so now even in the simple example, you can already show a very interesting relation between these Berry phases now and the von Neumann algebra, which, because we're doing quantum mechanics here, we are just talking about type 1 von Neumann algebras. And in fact, we can calculate the Berry phase from the symplectic volume of the entanglement orbit, sorry. So in fact, we can obtain the reduced density matrix from this matrix P. So essentially the reduced density matrix will be the square of this diagonal matrix. And but it's convenient to write it like this, because then we get other points on the entanglement orbit from this matrix Q. And so U is now just essentially an SU2 transformation, which involves the Pauli matrices as generators. Again, here we see there's two different patches, and there's one covering one side of the sphere and the other one for the North Pole and the South Pole, which then would amount to changing one sign here. And so then we can calculate the connection on this orbit, which is given by this expression here. And now we just, for our simple model, we insert all the parameters. So theta and phi are again the parameters of our SU2 manifold. And then the symplectic form looks like this. And the Berry phase is now, as I explained before, the symplectic volume. So it's the integral over the symplectic form. And what we find is that it's proportional to sine alpha. And so now we see that, and there's two interesting cases. So when alpha is 0, then obviously the Berry phase vanishes, but it also vanishes when alpha is pi. And so then, which corresponds to the maximally entangled state. So also in the maximally entangled state, the Berry phase vanishes. And so now the relation to the von Neumann algebra comes from the fact that we are looking for a trace functional, which is a linear functional, which has this, which is supposed to have the cyclicity property to be a trace. And so here we have a trial function where we take some elements of the left-hand side SU2 algebra and calculate the expectation value. And if we do that, then we see that if we evaluate our trial trace functional on a commutator, we get this expression here. And so from the discussion on the previous slide, we conclude that actually the trace functional on the commutator is proportional to the geometric phase. And so that's a very nice result. And so we see that, so for F being a meaningful trace functional, the Berry phase has to vanish. And this happens precisely both when there's no entanglement, but also for the maximally entangled state. So, and that's a very nice result that we can later also see in the black hole context. Okay, let me briefly mention that we can generalize this approach to infinitely many spins using these particular states. And so essentially we look at then infinitely many combinations of pairs. And so for each of these pairs, we can then define another Berry phase. And so then we obtain the TFD state for 2 copies of an infinite collection of spins, and the temperature is given by the entanglement temperature. So that in general will give us a type 3 von Neumann algebra, just because there's infinitely many degrees of freedom. And what is interesting is that we can again show that these geometric phases vanish, all of them vanish for maximal entanglement. And in that case, then we find an example where for a state where we can realize a type 2 von Neumann algebra. So the simple model that I showed you for just 2 spins in this infinite dimensional spin case, you can also use it to go from type 3 to type 2 von Neumann algebras. Okay, so now let's go to black holes and this eternal ADS black hole that I mentioned before. And so now, in fact, it's precisely this fact that we don't have a global killing vector in the presence of a wormhole. So that leads to a non-exact symplectic form, which then in turn gives rise to a Berry phase. And that will precisely give rise to this non-factorization that I was mentioning before. So the important point here is if we look at this eternal black hole geometry and a state given minus blue line, then there's 2 possibilities to evolve here. So one is with the sum of the 2 Hamiltonians on the 2 sides. And so that's a true diffeomorphism that will give rise to a non-trivial Berry phase, whereas if we evolve with the difference between the 2 Hamiltonians, this is a symmetry, and the state doesn't get transformed, and so this is not. So this will always give a vanishing Berry phase. So the fact that we have this non-exactly symplectic form arises in the following: that there's a mismatch in time. So if, say, there's an observer on the left-hand CFT and the right-hand CFT, and both of them dive into the into the wormhole, then they would see a mismatch in their times, which is called delta. And this delta is actually the gauge parameter that now enter these transformations here. Okay, so in this very simple example, we get something very similar to the quantum mechanical model that I showed before. So we have time translations at each boundary, which, because they show up in the e to the IHT quantum mechanical formalism, they correspond to U1 symmetries. Then, however, because there's this bulk asymmetry from the difference of the 2 Hamiltonians, there's actually, we mod the symmetry by U1. And so the bulk modular space has actually this non-factored structure. Okay, so this is a kind of factorized symmetry, but then due to this bulk asymmetry, we get a quotient here. And so then we have a non-factored structure. And so this is this circle is parameterized precisely by this time shift parameter delta that we see here. And so we can write down a Berry connection for the TFD states in the field theory language with this particular unitary transformation, and then we see that the Berry phase here is actually non-zero due to this non-exact symplectic form. And it's proportional to the geometric phase of the bulk modular space. And so this actually signals that we have non-factorization here. So let me just summarize what I said about these TFD states. So and extend it slightly, because what we can also do is that we consider these slightly generalized TFD states, where when we insert a phase here, the phase given by this expression here, with En the eigenvalues of the boundary Hamiltonians. And so, as I mentioned before, this gives rise to a non-zero Berry connections for a diffeomorphism where we sum the 2 boundary Hamiltonians, which I calculate here for you. And so it's really this phase parameter that really gives rise to this gauge parameter that allows us to define this geometric connection. And on the other hand, if we do this for the symmetry, so this is the difference between the 2 Hamiltonians, then this connection actually vanishes. And so something recent that we are doing is some work in progress with Shobik Banerjee and my student Jonathan Kahl, that we can actually relate these generalized TFD states to black hole microstate counting. So for these generalized phase-shifted states, their Berry connection, they can be thought of as microstates of the internal black hole. And so now the interesting thing is that they are equivalent for the boundary observers, and this is actually what maybe explain the different dimensionality of the bulk and boundary Hilbert spaces. So the boundary also for any alpha, the physics is the same, whereas in the bulk, these states are not the same, and that's related because in the bulk we have this non-exact symplectic form. And so what we're doing at the moment is to calculate the black hole entropy.
I have a question here.
Yeah.
Johanna, maybe I'm getting confused. You said in the bulk, these states are not the same. But in fact, for any bulk observer who's doing intrinsic measurements in the bulk, all of these time-shifted states are the same, right? I mean, the difference between them is just how the bulk time is glued to the boundary time. Because as you said,
yeah,
all
okay,
of this is
good.
diffeomorphism.
Yeah, I agree with you. So I think I just wanted to cut things short. Yeah. So what you said is exactly correct. So it's the way how you glue to the boundary is different. Yes, I totally agree. But from our formalism, what is the major difference between the bulk states and the boundary states is that in the bulk you pick up this non-exact symplectic form from this time singularity at the horizon. So I think that's my major point I want to make here. I hope that helps.
Thank you.
Okay, should I go on? Okay.
You may. Yeah.
Okay, good. So what we're doing at the moment is to calculate the black hole entropy from the overlaps of these phase-shifted states, and this seems to work well. And so there's a matrix model calculation involved, but we can borrow some approach of this nice paper here. Okay, so for those of you who are, I guess most of the audience is familiar with the recent work for Neumann algebras, and so in particular in this paper by Witten, it was shown that if 1/n corrections are included, this gives rise to a type 2 algebra with the vanishing center. And so this fact that the center vanishes, we can now phrase in a way that the Berry phase or the geometric phase is actually absent. And that allows for a transition from type 3 to type 2. Now we have a similar story here, and just phrase in more geometrical terms that so if there's non-factorization, it means we have a non-zero geometric phase, and that means we don't have a phase definition, and then it means we have a type 3 for Neumann algebra. And in the exceptional case that the state is maximally entangled, then the geometric phase vanishes and we get a type 2 for Neumann algebra. So we can rephrase this approach with the center and the cross product also in terms of this geometric language. Okay, so and also okay, I guess what I wanted to say, to coming back to discussion we had before, what I wanted to say, I mean, again, if you calculate the path integral for the boundary states, you only have these non-factored contributions, but in the bulk, there's these wormhole-like contributions arising, and here we just trace them back to the fact that there's this non-exact symplectic form. So that's, I guess, what I wanted to say here. All right, but there's also, yeah? Was there a question? Okay, no. So what is also nice, I can make a connection to this physical property of missing information, and in particular, when the symplectic form is non-exact, then there's no global section for the entire system. And this means that different coordinate patches are necessary to cover the space. And then in physical terms, this means that an observer in one coordinate patch has no information about the other. And so this geometric approach also encodes this missing of information, which enters the entropy definition. Okay, so now let me say that so far I was mostly talking about ADS2 spaces, but similar stories also apply in CFTs. As was already discussed in this paper. And let me show you a beautiful, simple example where instead of looking at the full, I mean, you can do this for a full Virasoro symmetry, both in the bulk and at the boundary, but the principle already becomes clear if we just look at the U1 abelian Chern-Simons that's defined on an ADS3 space, as one was done in this beautiful paper by Mageno and collaborators. So now we are in ADS3, and so we have a wormhole. Okay, so if we just turn this, if we draw this conformal diagram in a slightly more physical picture, and then turn our wormhole by 90 degrees, then this is the outer, so the left side of the wormhole, that's the right side of the wormhole, and then now it becomes very clear that there's actually a holonomy because you can wrap around the other end of the wormhole. And so if we do this for an abelian Chern-Simons theory, then there's a holonomy that is defined like this. And now, as is well known, if you have a Chern-Simons theory in a three-dimensional space, you can also equivalently write it in terms of boundary actions. And in this simple abelian case, sorry, you just write it in this pure gauge form, and this mu can take two values called capital phi and capital psi, which are the boundary values of this scalar function mu. And then from the Chern-Simons theory in the bulk, we get boundary actions for these fields phi, psi, and the holonomy. And so that was already derived in this paper by Enno and collaborators, and well, essentially you get an action, but the key point of this action is that you get some contributions from the left-hand side, so the left right, so the left CFT, and some contributions from the right CFT, but now they're actually coupled to each other, and they're coupled by this holonomy. So they're not disjoint. They're really, you get a Hamiltonian for the entire system, and it's really this this geometrical point or quantity which relates the two to each other. And and again, you have a non-exact symplectic form. Sorry. So because you can now actually write the symplectic form, which you can write it down for the boundary phase space. And so the conjugate momentum for the holonomy is pi 0 is actually a Wilson line in the bulk. And then this is your symplectic form. So there's a contribution from the left CFT, from the right CFT, and then from this holonomy. And because it's non-exact, again, we have the structure of the symmetry. So assume we were doing a Kac-Moody U1 symmetry, then we would have such a group on the left-hand side and another group of the same type on the right-hand side. But due to the holonomy, then the quotient goes for the entire product. And then again, we have this non-factored structure here. Okay, so now you can do something very similar for conformal symmetry. So where you have SL2R on each side. So for instance, you can do this for the left hand and for the right hand side. For the left movers, just stick with the left movers, but on both sides, on the left and the right hand side. And then we get something called a Virasoro-Berry phase. And then you can actually map the symplectic form on the phase space to a symplectic form on the Virasoro group manifold with a coupling between both the CFTs. And again, the left-handed Virasoro morods on one hand side, they're just this quotient of the diffeomorphisms on the circle. But when the symplectic form is non-exact, which again is the case here, then again you get this non-factored structure in the bulk. And so you can do this independently of the symmetry. So this Berry phase can be defined for lots of different symmetries, in particular also for the Virasoro group. All right, so how many more minutes do I have?
Johanna, your time approximately factorizes into 5 minutes for talk and 5 more for Q&A. Okay,
perfect. So let me talk for 5 more minutes. All right, okay, so then let me talk briefly about this paper. with Giuseppe Julius, who is also a postdoc in Würzburg, and my student Pablo Bastero. And so the point of this paper was to look at further quantum mechanics models that also realize these von Neumann algebras and where you can actually calculate them explicitly. And so this is, let me quickly say that this is motivated by another program that we are following here in Würzburg, which is to write down a ADS-inspired duality on regular hyperbolic tilings of the Poincaré disk, as you can see here. And these tilings, they are characterized by two numbers, P and Q. So P is the number of corners in each polygon, and Q is the number of polygons meeting at each corner. And so if this is larger than 4, then you get a negative curvature and you get a hyperbolic space. So in principle, the program that we have is to establish a duality, which is just the same as, is equivalent to the standard ADS-CFT duality that we know and love in continuous space. But now to do this on these tilings. Okay, so then, of course, there's still a big question mark. I mean, we have some proposals here for a quantum chain at the boundary of this tiling that is actually constructed giving how the construction principle of this tiling works and depends on these numbers P and Q. And so now at the moment we also are working on how to realize a gravity theory on this discretized space. And some results that we have is to actually find a particular spin chain at the boundary that has two different types of coupling that are motivated by the construction principle, which is the so-called inflation rule for these tilings. And then we actually find our RG technique to actually solve the Hamiltonian that you get in that way, and then represent it as a tensor network, which again shares the discrete symmetries in the bulk. And so the key point about this tensor network is that it now really represents a ground state of a given Hamiltonian that we can actually write down. So it's not just a picture, but it's a true ground state, which is represented by this tensor network. Okay, but what's the relation to the von Neumann algebras? So motivated by this construction, we said, okay, can we also see these factorizations in this simple kind of spin chain setting? And so in that paper, we didn't take an infinitely extended spin chain, but we just took a spin chain with 4 sides. And so then we wrote down a Hamiltonian, which involves, so it's not quite an SYK model, but because it's essentially pair interactions here. But so we have this function H, and this function H here involves a hopping parameter mu and also a coupling J. And R is this relation between two different, so the key point is that motivated by these tilings, we actually have 2 different couplings, and we can analyze what happens if we change this ratio. And so this ratio is actually plotted on the left, on the x-axis here. So, and essentially here, this is the free energy. And again, so what we find here, here you can calculate everything explicitly. And so we definitely here also get type 3 and type 2 von Neumann algebras, because we look at a large n fermions with an infinite amount of components. And so we actually find a phase diagram or a phase transition as function of this hopping ratio. And it can be either a crossover or a first order or a second order transition. And again, so these plots now are just plots of the correlation functions that we calculate. Okay, so, and clearly here again, we have a non-factored structure that resembles a wormhole, and here we have a factored structure. And so here, the nice thing about this model is that we can work out everything explicitly. Sorry. And we can actually, by just calculating the density matrix, work out where we have the different types of von Neumann algebras. So here at the bottom, when the coupling constant J is 0, then we have type 3 lambda. So, and here we have type 2, 1, and here we have 1 infinity, and then here there's the critical point where it goes from a first order to a second order phase transition. And so it's a very nice model where, which is motivated by some holographic input, and you just by explicitly calculating the density matrix, you're in control of all the von Neumann algebras. You can see that there's transitions between different regimes. And so the fact that it's large n means that you get also, that you get phase transitions, and then also you get type 3 and type 2 algebras. And okay, so here's some explanation of how to calculate this entanglement entropy, but maybe in view of time, I would skip these technical details. So, I mean, you can essentially just explicitly calculate the entanglement entropy here. And okay, so again, this is some explanation of which type of von Neumann algebra you get in the different parts of the phase diagram. But okay, let me not go into detail, but I mean, so this goes back to some work which has already been around for quite some time, but it's very nice that we have this very concrete example, and that translates quite a few of these discussions for Neumann algebras in the context of black holes into some models that are very tractable. All right, so then in view of the time, let me conclude. So here I showed you that you can view the non-factorization of wormhole Hilbert spaces to be due to a non-exact symplectic form that results in non-zero Berry phases. And so that leads to a rich mathematical structure, which is, I mean, okay, I only showed you some aspects of this, but there's a lot of discussion about phase spaces and orbits and so on that enters all of this, which is present in both in the quantum mechanics and in CFTs and also in these wormhole geometries. And so that gives a new ingredient to study these relations between entanglement and geometry. In particular, these phases, they characterize the von Neumann algebras. So you can also realize this in more down-to-earth many-body models. And so as we now are discussing, there's also some relation to the black hole microstate counting. So thanks a lot for your attention.
Let's thank Johanna. Questions?
I wasn't quite sure whether you were making a completely general statement about the non-exactness of the symplectic form versus the type of algebra. Because if I do a free field theory on the plane that has an exact symplectic form, just basically a generalization of P dx, but then pi d phi or so. And that has a type 3 algebra. So that's an example of an exact symplectic form in a type 3 algebra. So are you claiming that in a general situation, there's supposed to be a relation between the exactness of the symplectic form and the type of algebra? Or did you have something more specific in mind? I was a bit confused.
Okay, yeah, that's a very good question. Okay, so I think what I think I'm still working at the level of examples. I'm not sure I can make a totally general statement. Okay, so certainly what I can say that both in the spin models and in this eternal black hole configuration, it is certainly the so maybe it's conditional if the symplectic form is non-exact, then you have a type 3 algebra. Okay, that doesn't mean that there's other cases. I mean, okay, I have to think about the example that you mentioned. Okay, so that seems to be an example where the symplectic form is exact, but nevertheless you have a field theory That's not excluded by what I said. But I think what I wanted to say is that in all the cases where you have such a non-exact symplectic form, then it leads to a type 3. Okay, and that was true in the quantum mechanical models and for these two-sided black holes. Now, of course, you're just talking about a standard free type 3 CFT. Yeah, okay,
okay, but if let me do then a different example. So suppose I do the quantum Hall effect where the phase space is a torus. The symplectic form is basically the volume form on the torus. So it's not exact, but it's a finite dimensional quantum mechanical system whose dimension is determined by sort of the volume of the torus in Planck units. So that has a type 1 algebra, but it has a non-exact symplectic form.
Yeah, okay, yeah, okay, so that's a very good example, and this is something I really would like to understand. I mean, it would be very nice to kind of have a toy model of a wormhole by using a quantum hole system. I totally agree. So I think the issue is there that here our integration space was always something which was genus 0. Okay, so when people talk about Berry phases in condensed matter, like in the example you say, as you say, the integration region is a torus, and I think for the quantum Hall system, the Berry phase arises. I mean, actually the form is exact, and the fact that you have a non-trivial Berry phase comes from your integration region, which is a torus rather than the sphere. Okay. So, and everything I was talking about here, our integration region was always genus 0. And, but I think what you're pointing to a super interesting example, and this is really something I would like to understand in what sense this quantum Hall system is different from the wormholes and how this torus integration region comes into the game. But okay, we haven't looked at this yet, but it's a very, very good point.
Thank you.
Questions? I had one question. Can you compute the Berry phase in your hyperbolic tilings where the symmetry group is discrete now and see non-factorization?
Okay, that's a super good question. And yeah, okay, we haven't done that, but I mean, all right, that question raises, I mean, it relates to a lot of points. Okay, so first of all, at the end, I showed you the spin chain, but that spin chain is just a Majorana spin chain, so there's no U1 symmetry, there's no symmetry. I mean, so this arguments with the Berry phase don't quite apply to this very last example I showed. I mean, there you can just calculate the density matrix explicitly, and then you get all these transitions between the algebras. Yeah, the point is that for these, it's very hard to say anything specific about the symmetries for these tilings because they're discrete, but they're infinite. And somehow mathematicians, they have studied a lot Lie groups and they have studied finite discrete groups, but infinite discrete groups. I mean, there are some results about their representations, but not really in a language that is easy to understand for physicists. And so that would be something very interesting to do, but I think there's still a lot of maths required to which maybe exists but has to be put in a language where we can use it here. So I would say this is a super interesting question, but it's not straightforward to answer.
Thank you. Other questions? Yes.
I think I'm still a little bit confused about what your definition for the Berry phase is. Like you defined some connection and some integrating over some symplectic form.
Yeah.
Just go back to those slides once. I mean.
Yeah. Okay. Yeah. Okay. So I guess here I mean, okay, for the sake of the talk, I cut things slightly short because okay. So here this is mostly for the SU2 example for the spins. Okay, so what should I say? okay, I don't want to spend too much time on this. Okay, so this is really something you should think of for the SU2 case. Yeah, so I'm really integrating over this SU2 sphere. It's not a general definition, but okay, let me very, very quickly go. I don't want to take too much of your time, but just so I have some maths backup. Okay, so if you want to know about how to define the Berry phase for say conformal transformations, I really recommend this paper by Oblak. And so there's this very beautiful formula. I mean, here in this paper, I don't think there was any entanglement. Okay, so it's just defining the Berry phases for the orbits of the Virasoro group. So this is very beautifully explained in that paper. So if you really want to understand how to define the Berry phase in a CFT, I think that's where it's explained. I don't think I have time to go into this now, but so let me say the example I gave at the beginning was really the example of an SU2 symmetry for two interacting spins. But if you really want to do it for the Virasoro group, then you have to go to this orbit formalism and of these coadjuvant orbits. So, yeah, and I really recommend this paper where this is very nicely explained.
Okay, let's thank Johanna for a very interesting talk.
Yeah, thanks very much. And I have to say again, I'm so sorry that I couldn't be there. As you can hear, I really was in bed the entire week, and I wanted to go to the airport to go to ICTS on last Saturday, but I really couldn't, and I had to stay in bed almost all week, and I was super sad. And I'm sure you had all a great conference, and thanks for the really great questions. And I would have liked to talk to everybody in much more detail, and I hope there will definitely be another occasion. And I wish everybody a nice end to the conference, and I hope you had a good time.
Thanks, Johanna. Please come, whenever you're better. Please, we'd love to have
yeah,
you
thank
in
you.
again.
Thank you. Thanks, bye-bye.
Bye, take care.